Okay, physics. So today we're going to go over some of your homework problems and as well as some um, ideas about potential and kinetic energy. Now, the reason for this is because I accidentally assigned you some extra work. I assigned you 14.4 when really you were only supposed to do 14.3. That other assignment was for AP. But no worries, we'll just get into it today and I will help you out by working through these problems with you. So, first thing we need to talk about is the concept of potential and kinetic energy. All right, so potential energy we're going to abbreviate as U, and kinetic energy we're going to abbreviate as K. Now, thinking back to any sort of pendulum or any sort of spring apparatus and simple harmonic motion, when is the potential energy at its highest? That's the question we need to be asking. What is U max? All right, so U max is going to be when the spring is most compressed or when the pendulum is at its furthest tilt. All right, so that's going to be at the beginning of the oscillation. So you see here we have a graph. It goes from 0 to 1 oscillation, and then it has the amplitude on the y-axis. So U max potential energy, highest potential energy, is going to be right about there. Now, in simple harmonic motion, when we swing all the way to the other side, it is also going to have a U max of potential energy. So it's going to swing back or oscillate back to the same height, same amplitude, and be back at U max. Now, one thing we need to think about is where is K max? All right, so where is the kinetic energy at its highest point? This is actually going to be in the middle of these 2 points. So if you're thinking about a pendulum, it's going to be right when the pendulum is perpendicular to the ground. If you're thinking about a spring, it's when the spring's at equilibrium length. So that's going to be right about in the middle of the oscillation. Right here is going to be K max. All right, now, what happens in between U max and K max is an exchange of energy. So in between these 3 points, there's an exchange of energy. And what we have to keep in mind is that energy for a system is conserved. So there can't all of a sudden be more potential energy than U max, all right? It's the maximum amount. Likewise, there can't be more kinetic energy than K max. So this is the ceiling of what's possible for the system. What can happen, though, is that some potential energy is converted into kinetic energy. So if we were to take from U max and subtract out some potential energy, we would be left with just U. All right, so what this means is as we convert potential energy into kinetic energy, we still might have some left over, but it's going to be less than the maximum value. All right, likewise, if we were to take or add some potential energy to K max, we would end up with some amount of kinetic energy. So if we were to convert that kinetic energy into potential, or some of it into potential, we still have some left over, but it wouldn't be as much as the max. It would be less. All right. So now, how does this look on a graph? Well, if we converted all of the potential energy into kinetic, so if we subtracted K max from U max, K max, and we were going to subtract that from U max, what would it equal? Well, if you're looking at this graph, K max and U max are actually the same value because this is the ceiling for the system. Energy has to be conserved. So Kmax minus Umax would actually equal a 0 value for potential energy. In other words, when we convert all of our energy to kinetic, there is no potential energy. So let's go ahead and graph this out, right? As we convert the potential energy to maximum kinetic energy, it's going to approach 0. Right? And then as we convert the kinetic energy back into potential, it's going to go back up to U max. What about kinetic energy? Well, if all of our energy is in potential energy, that means we have no kinetic energy available. All right, but as the kinetic energy goes down, or as the potential energy goes down, the kinetic energy is going to go up because the energy of the system has to be conserved. Right, so we get an arc like that. And so here we can see the relationship between potential energy in red and kinetic energy as it goes through one oscillation. Now, there are two formulas for describing this kind of phenomenon. And they are as follows. All right, the first is the formula for period, calculating the period of a simple harmonic oscillator. You calculate the period by multiplying 2 pi by the square root of the mass over the spring constant. All right, so that is our formula for period. And then for frequency, which is the same as 1 over period. So remember, F equals 1 over T. We're going to see that in this formula. F is going to equal 1 over 2 pi square root K spring constant over mass. All right, K stands for spring constant, M stands for mass, and here are our two formulas that we're going to work with. Now, a couple of observations about these formulas. Number one, there is no place for amplitude in them at all. That means that the period and the frequency only depends on mass and the spring constant. Those are the only two variables we have in the formula. So we can adjust the amplitude all we want. It's not going to affect the frequency, and it's not going to affect the period. All right. So changes in amplitude aren't going to matter for frequency and for period. All right. We do have an effect for the spring constant, and we also have an effect from the mass, but these are different. So since they're inverted, some interesting trends are going to come about, right? And we'll go ahead and take a look at those in problem 17. So in problem 17, we're asked a series of questions on what would happen if we adjusted a simple harmonic oscillator in a couple ways. So a block is attached to a spring with an unknown spring constant, and it oscillates with a period of 2 seconds. So we're going to make a note up here that t is equal to 2.00 seconds. All right. Now we have A, B, C, and D. So A, B, C, and D. All right, and then A wants to know what happens if the mass is doubled, or if we have 2m. All right, what happens to the period if the mass is doubled? Well, there's a couple of ways of thinking about this. One way is that we already know that the period is 2 seconds, so we can plug that into our formula. So period is equal to 2.0 seconds, and that is that 2 seconds is equal to 2 pi times the mass, whatever it is, divided by the k, whatever it is. All right, now we want to know what happens if we sub in 2m for this number. Well, assuming that this is all going to equal the same thing, it's just going to be double, we can say it's going to change by a factor of the square root of 2. So any change between this mass and double the mass is going to be a change by a factor of this number here. So if we were to multiply 2 seconds times the square root of 2, we should get our change. All right, so we multiply 2 seconds times the square root of 2, and we get a total period of 2.8 seconds. All right, now the answer in the back of the book has a bit more precise answer. I'm okay with significant. We're going to get off at the 10th and using significant figures in that way, so no worries there. All right, so what we did was we found a ratio to compare it to, and we're able to multiply the total period by that ratio. Now, for section B, what happens if the mass is halved? So in this, we're doing something slightly different. Rather than taking 2m, we're taking 1/2 of m. All right, so let's look at how this is going to affect the ratio. The last ratio was doubling the mass, and we affected it by a amount of square root of 2. This time, we're going to be affecting it by a ratio of square root of 1/2. All right, so if we take square root of 1/2, multiply it by our standard period of 2 seconds, we get a grand total of 1.4 seconds. All right, and so it's exactly half of double the mass, which makes sense. So especially since we don't have a mass to work with. But again, we find the ratio and we multiply that ratio by our period. Okay, now we're going to get into amplitude for C. What happens if the amplitude is doubled? Right? So the amplitude is not on this formula. You don't see A anywhere. All right? A is nowhere to be found. And so that means that the period would not change as a result of a change in amplitude. So if the period doesn't change, that means it's going to be the same as the one we were given. So the answer for C is 2.0 seconds. All right, lastly, for D, we have to deal with the spring constant. So what would happen if the spring constant is doubled, if we had 2k? All right, well, that's actually the same thing as taking half of the mass, right? Because we're just keeping the k the same and dividing the mass by 2. That's the same as saying 1/2 m, right? 1/2 m is the same as 1m divided by 2, or just m divided by 2. So that answer is going to be the same as B. And so we don't even have to do any math. We can just say 1.4 seconds. All right. So you are working with estimations and approximations. It's definitely a math-minded question. But if you just can abstract it out to simple terms and think in ratios, then it is pretty straightforward. Lastly, really quickly, let's do problem 18, and then we will call it good. Now, for problem 18, we have a 200-gram air glider. 200 gram, that's going to equal 0.2 kilograms. All right, so we have our mass. Now, this air glider is going to be pushed 10 centimeters against a spring and released. A student with a stopwatch finds that it takes it does 10 oscillations, 10 OSC per 12 seconds, right? And that's going to be its frequency, because frequency comes in units of oscillations per second, right? We want to know what is the spring constant, so K is our unknown. All right, so formulas we have that involve K. Well, we have frequency is equal to 1 over 2 pi times the square root of K divided by M. All right, we have the mass, that's good. We have the frequency, that's good. 2 pi is just a number, and K is our unknown. So we can actually work it out with this formula. So let's go ahead and start by isolating K. Now, to isolate K, we need to first divide over or multiply this right side by 2 pi. Right, so we're going to multiply both sides by 2 pi. 2 pi here, 2 pi here. These are going to cancel, and then that's going to give us 2 pi f. All right, now we have to get rid of the square root to free up these, or this fraction here. So we're going to square it. All right, that gets rid of that. We square both sides. Good. And then now we have to multiply by the mass. So we multiply by the mass to cancel that out. And we get m times 2 pi f squared is equal to K. All right, so we have our equation all set up. Now all we have to do is plug in the variables or the numbers. So first thing is to put this frequency in units of oscillations per second. When we divide 10 by 12, we get 0.83. So we will use that 0.83 in our calculation. So we have 2 pi times 0.83 squared, and then times the mass. We're going to want that to be in kilograms. So we will multiply it by 0.2, and then that's going to be our constant, which when we multiply all out should come out to 5.44. Right, so 5.44, spring constants come in newtons per meter, so that's going to be our unit there, and that should be your answer for number 18 as well. All right. So go ahead and review this section. If you already got in on the homework and see something incorrect, you can feel free to fix that and resubmit the assignment. Yeah, also just review this section. We're on the home stretch, 3 weeks left, I believe. So keep pushing strong, guys, and I will talk to y'all later.